Hey everybody, we are back and we have the camera going. Gracie wants to know about visualization number 6. Let's talk about visualization number 6. When is visualization number 6 due? Let's go take a look. I think it's going to be decision trees, right? Visualization number 6 is decision trees. I'm going off of that assumption right here. I'm like going off the timeline. Visualization number 6 is decision trees. It is Friday, March 12th, next Friday. So we'll be covering decision trees next week, but let's do it. Can you go with the write-up for visualization 8? Yeah, let's do that afterwards. You got it, Sarah. Let's go right here, visualization number 6. So decision trees, and this is a really good kind of intro lecture. Let me bring over the screen for this. We got the file downloaded for this, and we should have everything up and going soon, doing some visualization talk. Let's go ahead and start talking through this. Okay, let me bring back up my screens right here. I need 3 screens. I need 4 screens. I need 5 screens. I've got 3 screens, but I'm not always using the third. I need more screens, more confident models. Hey, Mubarak, good to see you here. Excellent, good to see everybody. Let's hop over here to the main screen. Okay, I've got another monitor over there, but it's not always hooked up. It's just I don't have the desk space I found out, so I use it sometimes. I use it for the camera over there. Ah. Oh my god. Okay. So with this right here, let's take a look. We have here visualization number 6, decision trees. Using the data set, this is the data set right here we'll be using. You'll want to download it. Take a random sample of 400 plus the last 2 of your UTID. Make sure to take a random sample. Create a decision tree using analyze, predictive modelings, partition. Use Q18, anticipated starting salary, as a response variable, and the rest of variables as your prediction variables, except for the specific variables which should be excluded. So let's talk about a decision tree for a moment right here. And let's make sure we understand what's going on with decision trees. Let's bring up the notes. Decision tree notes, 2 seconds. Class is not over. I just put in here. Decision trees use what kinds of variables? Decision trees are going to use categorical. We'll go to notes. Decision trees are going to use categorical and quantitative variables. We'll go through the notes next time, next class. We shouldn't use identifiers for decision trees or things that act like identifier. And so some categorical variables, like these are the good ones. Let's highlight the good ones right here. We can do this real quickly. These are the good variables we put in decision trees. We put these into decision trees, categorical and quantitative. We do not put identifiers or things that act like identifiers. And so I'm not going to say the answers, but there's a really quick and easy way to find the answer. Now, the problem is I've seen a lot of people, like, I'm not going to say the answer, but I'm not going to point to the answer here. So the newer versions of Jump, which I think everyone should have downloaded now, have a button right here where you can view the data. And it's probably going to be a little interesting. Not as interesting as I thought. We'll do this, though. Awesome. Yeah, that's going to make it clear. Now, some people sometimes put down things like, let's go to one that I usually see that people say it's an identifier, like anticipated starting salary. Sometimes people will tell me anticipated starting salary is an identifier because it has a lot of, or could act like an identifier because it has a lot of unique values. But I need to hear from the chat right now, anticipated starting salary. This variable right here is a what kind of variable? Like Jump tells you a few things. We're making the screen look all crazy. Anticipated starting salary is a what type of variable, which is why you see this graphic right here. Anticipated starting salary is a what kind of variable. It's why we see this graphic right here, kind of a test 1 topic. Anticipated starting salary is a what kind of variable. And it's why we see that histogram. Anticipated starting salary is a what kind of variable, and it's why we see that histogram. So we've got anticipated starting salary as a variable we're going to put in our decision tree. And what kind of variable is it? That's a huge hint. And the histogram is a huge hint. Quantitative. Nice job right there, Grace. It's quantitative. So the only things we do not want to include are identifiers. We don't want to include identifiers. So does that look like an identifier right there? Does that look like an identifier? Like, does that look like an identifier? I mean, as far as things being identifiers, it's pretty clear that that's an identifier. So I'm going to delete it. And then we have things that act like identifiers. So that was an identifier. It clearly said this is an identifier. And although someone might be pointing out to me right now, wait a minute, it says quantitative over here. We won't really do much analysis with this. So technically we could switch this over to a categorical. We could go none. Yeah, it's probably good right there. We're not really going to use it. It's not going to really have any type to it. And you could also make the case that aren't identifiers just groups of one, and that even makes it look more like it's an identifier here, and we're not going to analyze that. So this is kind of what we're looking for. This is a hint to what we're looking for. So we want to see something like this right here. And if you look, these don't look that bad. Here's gender, here's born in Tennessee, here's on campus. Those don't look that bad. Anything jump out to people right here on this screen that could be an identifier? Any numbers, cue anything? This is your chance to help out your classmates, especially on this screen right here. Does anyone see anything that jumps out as, looks like maybe it's an identifier? Like any sort of variables on this screen currently that's like, ooh, that looks like that is a categorical variable that has a lot of levels. So some categorical variables act similar to identifiers if they have a lot of levels. These should be excluded. So we want to look for a categorical variable, which we're on 11 through 19. So that's currently what's on the screen right here. So there's the names. And then we see some of the coloring right here to help us with categorical quantitative. So we're only really focusing in on the categorical ones. We're only focusing in on these. Like make sure to only be looking at those. The other ones are quantitative, and we see histograms respectively. So histograms are not, that's just quantitative data. So we don't have to worry about those acting like identifiers. And an identifier is something that is unique for each and every observation. Things that act like identifiers are going to have lots of levels that, too many levels that almost act like identifiers. They're not really identifiers, but they would act like it. So it's your chance to help out your classmates if you want with maybe a current variable on the screen acts like an identifier. Now it is not an identifier, it just acts like one. And so any ideas on this screen on something that might act like an identifier? Now it wouldn't be an identifier. Any of the possible columns we have that might act like an identifier, and you can just put Q whatever. Any of these columns might act like an identifier? Like, remember what it means to act like an identifier. Like, what does it mean to act like an identifier? Well, an identifier is unique for each and every observation, so this would never ever repeat. This is an identifier because it never ever ever repeats. And then things that act like identifiers are going to be categorical variables that have lots of levels. So we've highlighted only the categorical variables on the screen right now. And then we need one that has too many levels that kind of would act like an identifier. Think about this. Like if we ask people, what city were you born in? That might act like an identifier. Exactly. Great job right there, Grace. This one acts like an identifier. And I like that you put that. Yes, Sarah, you got it too. The question mark is like, I think it's this one. You're 100% right. 100% right. Let's throw some 50 points to the chat. You're 100% right that acts like an identifier. So it's not truly an identifier. It just acts like one. Anything. I mean, those look kind of good. Not that many levels. Ooh, look at this right here. I mean, okay. Well, that's the answer. Happy Thursday, I agree. So this also acts like an identifier right here. You can see a lot of people like Snapchat, but what do you notice about this especially? What do you notice so let's go ahead and analyze distribution. You don't have to do this, but let's look at those individuals. And what do you notice? Oh, I did the wrong one. I did major. Analyze distribution. Why do I have major still selected? I want to do favorite phone app. Favorite phone app. There we go. And here we go. So when we look at this, there we go. What is the difference? What is the difference? Oh, I see it now. What is the difference between, wow, and that's so interesting, the small difference right here, which was almost a 50-50 split in the way people spelled the number. And if we combine these, Instagram. I don't know if you guys have downloaded Instagram or Instagram. Wait. Insta. I can't speak. Oh my gosh. These are all the same, obviously. These are all the same right here. So we could probably identify this one person who made this typo because there's so many groups here that we're gonna have a lot of unique values. Does it make sense to everybody what it means in a decision tree when things act like an identifier? It's like a categorical variable with many, many levels could act like an identifier. So a categorical variable with lots of levels could act like an identifier. But quantitative and categorical variables are all good. These are all good right here. Quantitative and categorical variables, A+ right there. Those can be the X, those can be the Y. We want quantitative or categorical Ys, quantitative or categorical X's, but we don't want identifiers. Those are a no-no to start. Or we don't want categoricals that have too many levels. Those are unique categorical variables like this one right here that has way too many levels. This one over here does not have way too many levels. That's fine. it would be interesting to talk about how many levels is too many, but it would depend on how much data you had. And with almost 2,000 observations, we'll be fine on this. But this one that's way too many levels. It's got it's got like 300 levels. You can see it says like 287 others other than this one. I think if we change this, yeah, it changes to 280. If you could do this right here, you can almost see how many there are. Oh, well, let me do that. That's a bummer. 1, 2, 3. There's 295 levels, it looks like. Okay. So now that we know which variables not to include, I'm going to do this. Here's a good tip. Just delete them. You can re-download the data if you want. I mean, this is not a best practice, but I'm just going to delete them to delete them. Where'd major go? Let's delete original row number because we're not going to use it. I'm just selecting the column, and then I'm just going here and delete. And then we go here to major, and we just go delete. It's gone. Write it down, delete. Here we go. Major was destroyed by Brian Stevens, delete. So now we have, with those removed, we do need to mention those. Let's go back and look at our write-up right here. So, take the 3. Okay, we need to do the splits. So, so include a short write-up, the names of the predictors who are you excluded and the reason why. So we've already got that done. So we should talk about that and explain why. And the explanation why is basically over here. Like, remember, we're talking about categorical variables that have way too many levels should not be included because they act like identifiers. They're not truly identifiers, which identifiers are unique for each and every observation, but categorical variables with too many levels will act like an identifier, and identifiers are not used in decision trees. So we're going to predict starting salary. Now, I'm not going to predict that, and I need to take a random sample. I fear sometimes I don't do that, and people are like, wait. I'll do it correctly, 400 plus the last 2 of my UTID. And here's my random sample. Make sure you are using a random sample. That is key. And we're predicting a quantitative variable. So we're going to go here to Analyze, Predictive Modeling, and Partition. So that's Analyze, Predictive Modeling, and Partition. So I'll pause here on this screen. So now the way to do this really easily is to click Control-A or Command-A on a Mac, and we've selected everything. So now that you've selected everything, let's go ahead and drag everything over to the X. Now, I want to point out I have deleted the variables we don't want. So make sure you're not using your identifiers. Do not have the identifiers here. Do not put the identifiers over here. Identifiers or things that act like identifiers do not go over there. Let's drag these over here, and I need your help in the chat to tell me a quantitative variable to predict for my Y, and I'll show you how to get the quantitative variable up there. I need your help to pick a quantitative, just say Q whatever. You just can't pick Q, what was it? You can't pick the one we're doing. So pick a quantitative variable to predict. Let me see which one we're not going to use. We will not do Q18. Pick a quantitative variable to predict. I can't say which, I don't want to say which one specifically. Watch the video because I don't want to make it too step by step. I want double check. You'll delete the ones with too many levels. You'll delete the ones that are identifiers or act like identifiers. Major favorite phone app, identifier to start. Major favorite phone app, identifier to start. Anyways, Grace, yes. Does that make sense? So now that we've deleted the identifiers or things that act like identifiers, what do we have next? What variable are we going to predict? We can't. What variable are we going to predict? What variable? Q what? I need your help. I forgot how to do this. Brian, you always forget how to do everything, Brian. Why do you teach this class? You don't remember how to do anything. You're always asking us how to do it. Like, I don't know how to make a decision tree. It takes a whole bunch of variables. Decision trees take a whole bunch of variables. Make a lot of decisions. What Q are we going to predict? Now, we want a quantitative one because we're going to do one similar to the work we're doing. This will not be yours. Yours is going to use this one. But which one are we going to do? Which one shall we do? Q what shall we do? I forgot what quantitative means. These little color things over here might help me figure it out. That might give me some info. This one here, Q18 is quantitative. So I'm guessing that these other ones are also quantitative. So which Q number should we use? Q what? Q what should we use? I don't know. I need someone to tell me. What Q? Q something. Q what? Not QQ, straight up, no outliers. Goodness for correlation. Q what? I don't know. Q, which one? We're going to predict a quantitative Y. We don't have to predict a quantitative Y. We could do a categorical Y. But the assignment uses a quantitative Y, so we'll use a quantitative Y. And it's important to know that decision trees can predict quantitative Ys or categorical Ys. They can use quantitative X's or categorical X's, and that really goes back to this major important slide that they use quantitative or categorical Ys, quantitative or categorical X's. They do not use identifiers or things that act like identifiers, which are categoricals with too many levels. So Q what shall we predict? Q what? Q what? Which one? What is another quantitative variable? Also, one needs to type is Q this, and we just need another quantitative variable. What is another quantitative variable that we could predict? Q anything. It can't be Q08 because Q08 is categorical. We could predict Q08, but we're not going to do that for this one because we're going to do a quantitative prediction here. So this could work. We could put that up there. But what is the one we're going to do? I think chat's not frozen. I think. I might reload chat. Let me reload chat here, make sure it's not frozen. But pick a Q number variable right here. I am reloading chat. So put any Q variable number in the chat. I am watching the chat. As soon as we have a Q number variable, we will use that Q number variable. I think someone might adjust chat because I think I saw Mubot register it. It's so weird. Mubot sees things before me. Did Mubot see it already? 13. Thank you, Sarah. I don't know how Mubot's in the future. Mubot actually sees chats before they happen. Let's see. Q13. You are right. Yearly pet expense. Yearly pet expense. This will actually be a very good one. Thank you so much, Sarah. That's a really good one for us to do because watch this. So I want to point out what I did just so everyone can see. We're going to click yearly pet expense. Let me do this process from the start. When you get to here, you're going to select all the variables. Make sure your identifiers are out of here. And then you're going to drag and drop them in. Thank you so much, Morgan, right there. And now that you have them all dragged and dropped here, just to repeat, so we said this at the start, you'll hit Command or Control A at the start right here, Command or Control A, and now you've selected everything. Now you're going to drag and drop these over here. With these dragged and dropped over here, you're going to click once on the variable you want, which is going to be yearly pet expense for us. This is just ours, an example problem right here. And then you're going to drag this up. Make sure you do not have your identifiers. We have removed the identifiers, which kind of gives you a hint for which ones you need to remove. So with this right here, we're going to get a decision tree. So here is our decision tree, and we're doing yearly pet expense. We have our random sample, all confirmed. You kill me, Connor. You're awesome. Connor, you're awesome. Connor, you're the best. I appreciate your help, Connor. You come in and you bring so much positivity. And so we have right here, we're going to do 3 splits. 1, 2, 3, and we didn't get a symmetric tree, not the end of the world. I'm using Control Shift minus. Control Shift minus makes the output smaller. So this is Control Shift minus. I think it's Command Shift minus on a Mac. So what I'm going to do right here, make sure that's just a random number line. Boop. So let's go ahead and screenshot this. And this will be our screenshot of our tree. And so we're going to put this into a Word document. We're going to open up our 50th Word document and drop that into the Word document there. You can do it in multiple screenshots. I prefer just to zoom out. That was Control Shift minus or Control Shift plus and jump to zoom out. You can adjust this now and make this a little bit bigger. There we go. Okay. So I'm probably going to, and then I'll screenshot this. It's not the prettiest of trees. And there's that. And we have now screenshot everything we need. Screenshots are in here. You could technically make this smaller. Put that right there. Make this a little bit smaller. Not too small. You want to make sure your reader can read it. But on a page layout, that's pretty good. Like as a page layout, that's not that bad. This could be a little bit bigger. To kind of look at the things dimension, you can make them equal size. Look at it dimensionally and say, like, does this make sense? Does this look all right? If you zoom out to think about how it would look on a page if you printed it, I would say this looks pretty good right here. So with all of this, let's take a look. We've got it on a page, so we can just analyze it here. Do you allow trimming and force? Oh man, yeah. So we we do allow that. So here, let me mention what Connor's talking about. I am fine with this because we're just learning it conceptually here. So if you got something you didn't want, like I could force a split. So what Connor means by forcing a split here, this is what trimming is, or pruning the tree. So think about if you have this tree growing and you prune it down, you could prune the tree down, and that's trimming your tree. So the tree wants to grow this way right now, but I'm going to force the split this way. So wait, why can't Oh, Connor. Wait, can I not force a split there? I can't force a split, Connor, because these people have less than one pet. And so the mean is zero and the standard deviation is zero. This is such a unique instant, Connor. I've never seen, well, I haven't seen, I don't think I have seen this. But so, Connor, here's an advanced question for you. Why is there no ability to force a split right here? And the answer is right here. So this is such a great advanced question. I'm going to zoom in on it. Connor, why? I do know the answer, and I kind of said it a half second ago. Why can we not get this to split any further right here? And it all goes to what statistics is, and statistics is about analyzing what. Why can we not force a split on that anymore? We cannot. There's no ability to split, and it goes back to the definition of what is statistics. So I cannot force a split right here. I love this theoretical question. Why can I not force a split? Because it goes back to the definition of what statistics is. It's all about analyzing what, and there's no what there. It's all about analyzing what, and there is no what there. And it kind of makes sense. This at least makes sense when you think, there's no differences, there's no variation. Everyone in this group reports that they spend $0 on their pet. We're analyzing, let me zoom out on this so it makes more sense. We're analyzing how much money do people spend on their pets. That's what that says right there. We're analyzing how much money do people spend on their pets. And everyone in this group, every single person in this group, if I prune this, it'll be really easy to see. Every single person on the left group spends how much on their pet yearly. Every single person on the left, all 175 people here, and it's a good news that this is true for them, but all 175 people over here on average spend zero. And since the average is zero, there's no variation. And since there's no variation, we can't subdivide the group anymore because there's no variation. This actually explains all the variation in that group. And you can see it up here visually with all these people right here spending $0, and they own less than one pet. So when we say they own less than one pet, what does that mean? So we're talking about what this tree means right now. What does it mean that someone owns less than one pet? Like if you interpret that and you say, my friend owns less than one pet, what does it mean to own less than one pet? Like this group right here, these are their X values. So inside the tree, we're looking at their X. And so that means they what? Connor might have already put the answer there. So it means they own 0 pets. It means they have no pets. So these people have no pets, and then they spend no money on their pets, which would make sense. These people own 1 or more pets, but we can force a split by going here to force specific. We could also force it to split on number of pets owned. So that's what Connor was talking about, like forcing a split. So you could force it to split here too. And so we can say like, we want the tree to split here. So you can force splits. I'm okay with that with this assignment. If you do own it is number of pets, it splits on there anyways. Who would think that pets explains, ooh, and then it's tobacco usage, but what's the R squared increase? Connor, no joke. Connor, did you see this? Connor, I want Connor to explain what he thinks when he sees this right here happen. And actually, we'll show this visually here in a moment. Connor, like, what is your thoughts? Because I have a thought on this when I do one more split and I see this. And this is not forced. It's just the next split in the tree. And I'm going to see if it makes sense. It's a smallish group, I just noticed, I think. Yeah, it's a smaller group. But still, this is pretty interesting to me right here. So what's pretty interesting, and maybe Connor's noticing also, is there's a big jump in R squared, but we are seeing the group is pretty small. So maybe it's due to unique individuals, and we'd want some sort of validation on this. So Connor's probably saying, hey, Brian, you need a holdout. You need to validate your model on a holdout. Like Connor should be screaming that right now. Like, Brian, how do you know this model works on new data? You only have a training set right here. You don't have, are you cross-validating it? Are you using a holdout? I'm sorry, this is 201. We don't talk about cross-validation. We don't talk about holdout. We're just trying to tell them what a decision tree is, Connor. I'm sorry. I let you down. So, okay, back to 201 topic. So let's go down this pathway right here. is already placed with help with number 5 on the homework. I think which one is that, Sarah? Tell me which one it is, and we can do that. I think we're going to talk for a moment about visualization 8, and then we can talk about that, Sarah. Which one is this? How many folds? K fold 5, always K fold 5. Ben folds 5, K fold 5. I'm going to do a different decision tree real quickly because this one just talks about pets, and who would think that pets is a good answer for pets? It's a good tree, but it's a little too good. Let's predict someone's age right now. So we're going to predict someone's age. Very similar idea here. That we're going to use a decision tree to talk about someone's age. And I want you to look at this tree real briefly. I'm going to make it symmetric so that way it's easier to look at. I want you to think about this tree for a moment. So when you look at this tree right here, and let's zoom in on it, I want you to tell me about the people. This is interpretation of the tree right here. I would like for you to tell me about the people who are the oldest. I'd like you to tell me the qualities of the people who are the oldest. This is 100% on your assignment. I'd like to tell me, Terry Foltz, talking to Rick and Morty. Listen to Chaos Chaos, they got that song. It is a multiple choice question and the probability of them getting them all right. Yes, I can do that one here, Sarah. You got it. We'll do visualization 8, and then we will definitely do that. You got it, Sarah. Thank you so much, Sarah, for swinging by, and we'll do that one. I know which one that is now. We haven't done that one yet today. Tell me about the people. So you got 4 groups of people right here. Let's look at this. There are 4 groups of people. Group 1, Group 2, Group 3, and Group 4. So tell me about these 4 groups, and you have to trace like this to get to them. So which group? Just look at the data and tell me which group is the oldest, and then I'll describe it. So Group 1 has 103 people in it, and they follow this pathway. Group 2 has 49 people, and they follow this pathway. Group 3 has 262. Like 262 people meet these qualifications. Window key. What does that do, Connor? I'm a little afraid to hit it live on stream. What does that do? Like someone like logs into Connor's account. Like, what does that do? Windows Shift S. Too afraid of stream. Which group right here is the oldest? Oh, screenshot. Oh, that's cool. I didn't know that. Like it's a full screenshot. That would help. I always use, yeah, I never tried that. I'll have to start using that. Which of these groups is the oldest? Like we've got 4 groups right here. Which of these groups is the oldest people? And then let's talk about that group. Which of these groups is the oldest people? Group 1, Group 2, Group 3, Group 4. Which of these groups is the oldest? Oh, you can snip? That's awesome. I need to start using that. Windows Shift S. All right. I'll have to do it. I'll have to check it out. Which of these groups is the oldest group of people? Does anyone know which group is the oldest? So Group 1 has 103 people in it. Group 2 has 49 people. And we've got the mean below here, so that's probably going to be good information about which is the oldest. We have the variation in it, which is standard deviation. So which of these groups is the oldest, though, out of all these? And then we can see their characteristics. Like Group 1 right here and Group 2 live on campus. Group 1 lives on campus and has a GPA that is greater than or equal to 3.75. Group 2 lives on campus and has a GPA that's less than 3.75. This group over here, you could basically call the people who don't live on campus. They live either under a 10-minute drive, walking distance, 10 through 30-minute drive, or 30-minute drive. So literally, this is like, you can just classify these as on campus, and you can classify these people as off campus. Like these people are everyone who's off campus. So these people over here on the right are off campus people. And down here, we have another variable they're dividing on. You are right, Morgan. Group 4, because these are people who live off campus and are working. And I just want you to think about this. And like, I work during the summer, but these people right here are working 32 hours or more a week. And their average age of these 9 people who live off campus and work 32 hours or more a week, their average age is 23.55555. And this was the Y variable we wanted to analyze. Remember here in the graphic that we had, the Y variable is how old are people. And so this is a different one than we were doing before, but we're analyzing age. So when you go down here, you get the age. An important thing we should know is the leaf report actually gives us this information of the characteristics of the individuals. There's their, like they could be this drive, walking distance, all these things. And also they work more than 32 hours or more a week. Their mean age is 23.55555. And there were 9 people in this group. Does this make sense, Morgan, how to read this, like to see what this means right here as you travel down this path? and these are the X characteristics of the individuals, and this is the predicted Y value of the individual. So you go down here and you say, okay, these people live on campus, and they have a GPA greater than or equal to 3.75. There's 103 of them, and their mean is this. So hopefully it makes sense how to read this. Like you're just following down a path, and you're saying, like, let me talk about a certain like group of people. And you get down here to the group when you read their X variables, and then you get the Y characteristic, which is their age, which is what you're trying to analyze here, the variable you're trying to understand. This leaf report shows you the groups 1, 2, 3, and 4. And I want to point this out because it made more sense to me when I saw this. I hope this helps out a lot. When you see this, root absolute squared. Oh, what is that? I do not know that one, Connor. That's such a good question. Root absolute. So wait, if you were to take... Well, the root's going to remove the square, and you're changing it from RMSE to RASE, so the mean and the absolute. I don't think it's, I'll tell you this, I don't think it's root absolute error. Oh, it's at the top of the tree? Oh, what is it? I don't think it's root absolute error. Ooh, what is that? That's a good question. What is it? I didn't even notice that. Talk about output I don't look at. I'm always like, be able to understand all the output. What is RASE in decision tree? Oh, in jump, someone literally asked. You could be right. It makes sense. The square root of the mean squared prediction error, this is computed as follows. Is it not just... It might be root absolute error. Oh my God, this page is going crazy. RASE, the square root of the mean squared prediction error. It's the sum of squared error over the sample size. Wait, how is RASE different than RMSE? I've got a page up on it right now. Oh, they call it RASE now? No way. Why would they call it? Because you're averaging it. I think it is, because here's the error. Oh, I bet you're right. I bet you're right. Why are people calling it RASE? Just call it RMSE. Why are they doing that? I think you're right. I think it's average, because absolute didn't make sense to me, because absolute, like when you square it and then you root it, you'll get the absolute error. So like, and that would contradict, like, you know, we have two topics. I'm sure you know this, Connor. We have RMSE and we have RMAE, which is mean absolute error. So yeah, I think it mean root average squared error. I know, right? What are they doing to us? Why are they changing this to an A and making it... So, and that would make more sense with mean and average. So jump is maybe just trying to be unique, and that is the typical miss the model makes when predicting someone's age. So hey, 320, if you're listening in, this is the typical miss we make when predicting someone's age using this model. We're typically off, or on average off, by about 1.17. And since it's RMSE, we have identified it. If you notice right here, I want to point this out, that I've highlighted group 1, group 1, group 2, group 2, group 3, group 3, group 4, group 4. And still here at the top, we don't have that graphic. It still works the same way that the groups go in this order. So one last thing to know for this output, one last thing is that we also need, I believe, I'll check to see if it's on there. We need the split history, or at least we need to understand. So we do have a bit of a weird split history because of what I did, but the split history shows the increase in the R squared. So this is an important topic that could be on your test. The split history shows the increase in the R squared after each split. And how many splits do you think I should do technically, Connor? Like if you were to see this, I know you and I both want for there to be a training and holdout, but probably looking at this data right here, where would you split this tree to? I have an idea, and I want to see if Connor confirms my idea, and then I'll explain why Connor and I maybe came to the same idea. I think I know where I'd split it. Where would you split this tree, Connor? Or where would you stop splitting this tree? And don't do this for your assignment. You're supposed to have 3 splits, because you're just understanding what are decision trees. You're not trying to optimize decision trees like we do in 320 and 474. It's just like, what is a decision tree and how do we use it? And then in 474, we go more in depth. You go to 4? Maybe. we really need to look at the cross validation, right? Cross validation would decide it for both of us. I'd go to two. I'd go to two. Connor wants 4 splits. I want 2 splits, and neither of us could argue with the cross validation. Like Connor wants 4 splits. Connor's going to go with an R squared of 32%, and Brian's going to go with an R squared of 26%. Connor, your tree might be what? My tree might be what? So just to review concepts, Connor, your tree would be more possible of having this problem. My tree would have more problems with having this problem, maybe. And both our trees could be this technically, but your tree would be more likely to be this. My tree is more likely to be this. So just because yours has more splits, more complexity, yours used more information. So yours could, yeah, exactly. Yours could be more overfit. It might be the right answer. We need to look at some cross validation for that. So I might have underfit my tree though. So I might have underfit, like I could have done better. I could have taken more information out. So it's the bias variance trade-off. Like your tree is going to have less bias, but more variance, bias variance trade-off. My tree is going to have higher bias, but lower variance. Like my tree will work more similar. 474 topics, but the right amount, that's so hard to figure out. And we need cross-validation to figure that out. So good reviews, like working data on new models. I think that's got it. Let's just take a look at the notes right here. Connor, I really enjoy talking about this. So like at a decently, like at the 474 level, it's so much more fun. Like, I mean, like to like do like, oh, stat to one, there's so much more fun to come. Like decision trees are such a big topic. Like Connor, have you seen where people are using things like decision trees or, you know, like boosted models that are taking tons of variables and finding out these unique relationships? Like this is a lot of intro statistics courses would never show you this kind of stuff, but this is like the super most powerful things. And I just want everyone to think about what we've done here theoretically. What we've done theoretically, and I'll talk about the answers real quickly again, is we've taken all of these variables right here, and we've said all of these variables get the chance to explain one variable. Like all of these variables can try to explain gender. And then we're making a model right here, and this will look like a mosaic plot. We're making a model to try to explain it. If you notice right here, we're asking the questions like, do you use tobacco? And these people over here either vape or don't use tobacco, and they're more female than male. These are the people who are using dip, chew, snuff, tobacco, multiple tobaccos, smoking cigarettes, and or pipes. And there's a lot more males over here. These people over here are the ones who vape or don't use tobacco. And then this group right here spends less on coffee. This one spends more on coffee. And boosted trees, oh yeah. Let's see if we get another good split. So that's what people drink. I carry a refillable water bottle. So this is your primarily female group. This is your primarily male group. Let's split this one more time. So, I mean, this is just the way the data goes. And it only explains 20% of the variation. But I want us to think about this. This model says if somebody smokes a pipe and is like conservative, you know, it's conservative or moderate, because we actually didn't have enough of the views to split more. But if they're conservative or moderate and they smoke a pipe, they're probably male. There was one female over here, no joke, which is so awesome to see in the data set. It's like, oh, it's so awesome when like it splits this way. So let's go over here to the leaf report, and crazy output. But you can see there's the one female in the first group. So there were 39 people, and there is one female who is moderate or conservative, who smokes in some way that is like pipe, tobacco. They either use dip, chew, snuff, multiple tobacco products, cigarettes, and or pipe. And then their social views are conservative or moderate. So there was 39 people. One of those people was female and 38 were male. And we're looking at this group over here. You can see all the bottom leaves. There's 1, 2, 3, 4, 5 leaves. And then you can see the information on these individuals right here. And it got a little bit long. So we don't try to make your output look this crazy, because interpretations can get pretty crazy on these. You can see there's 4 females here, 3 males there. And that would go into this split right here, where we have people who use any of these tobacco products and they are liberal. And so pretty interesting. I don't know. I love data. This is real data, and it's just going to do what data does. But that's got it. Let's talk briefly about the write-up for the last one. So great job. People working ahead. Awesome work. So let's go down here to visualization number 8. Sarah, are you here I can answer some questions. Where's visualization number 8? So Sarah, if you're here, let me know. This is like, I think everyone's like, 320 was here this morning. I think 201's pretty like, wait, what did I just download? Everyone's pretty tired. Everyone's like, oh my gosh, Brian, we had the test this week. So good review, Connor, right here. Awesome, Sarah. And I think was it you, Sarah, who asked about Visualization 8, or you asked about the My Pearson one, right, Sarah? Did you ask about the My Pearson? Because I could do that right now. If other Sarah's not here, I'll make sure it's in the video for her. But you were asking about homework randomness, I think, and you were asking about the multiple choice one. Access denied. Well, I can't do it anymore. I'm just kidding. I'll do it. I have to relog into Pearson, it looks like. So I'm loading up Pearson. Really? I should call up my friend. I don't even know his number anymore. You think he has the same number from 20 years ago? Gosh, I need to stop talking about that kind of stuff. Does my friend who I knew 20 years ago have the same number? 21 years ago. Gosh. No. Oh my gosh. When you turn 42, do you get to you're double the age it like required to drink alcohol. So it's like, it doesn't mean anything though. It doesn't matter if you turn 21. I guess you can like rent cars and you can like get lower insurance rates and all this stuff. Awesome. Let's find that one for the homework. I'm pulling that up and then I'll put the other question in for other Sarah. So here we go. Okay, wait. No, that's not the one. Is it, you said, Sarah, your question was about, it's a multiple choice question about the probability of getting them all right. This one right here, right? Okay, should be on the screen, am I? Yes, I've been on the screen this whole time. So it's a multiple choice question about getting them all right. So it's this question right here, and let's take a look at it. I think can we copy these? Oh my gosh. Maybe you want to copy them that way. So with this question right here, I'm gonna make this a little bigger, and I'm gonna go here and I'm gonna copy this. So however you want to copy them, perfect. Now we're gonna bring it over to Microsoft Word, and we're gonna work on this problem. So let's talk about this multiple choice question right here. Now, let's say, you know what's really interesting? We're going to do this like the stat tool one way, then we're going to do it the 320 way. And I want to maybe give some people some positivity for the test. So check this out. So when you study for a multiple choice test, you could, really understand the material and you could have the probability of 80% of the time getting it right. So that means numbers 0 through 7 represent getting it right. Connor remembers it. Nice. So we have 0 through 7. Oh, you were doing this on the board. I remember that. Means right. And 8 through 9 means wrong. We are using a simulation here to simulate what would happen if you took a multiple choice test that had 5 questions, and we want to see how often you get them all right or how often you don't get them all right. So not all right. Yeah, that's what we're going for. How often would you get them all correct? So check this out right here. Let's go and see if you get them all correct. So on the first thing, Sarah, you get a 0. Does that mean you got the first question right? I want you to look at this right here. Is this in 0 through 7? Did you get the first question correct? Did you get that first question correct right there? Did you get that first question correct? So did you get that first? You got a 0, which we just simulate a 0. And does that mean you got that first question correct? You did. How about the second question? And the third and the fourth and the fifth and the sixth? Did you get all the questions correct right here? Did you get all the questions correct? So 0 means you got it right, 2 means you got it right, 5 means you got it right, 4 means you got it right, 1 means you got it right, 1 means you got it right. So all those numbers are contained between 0 and 7. So what does this mean right here? That means you got them all correct. But what do you notice about the next simulation? In the next simulation of 6 questions, how many do you get wrong and which question? So in the next simulation, how many do you get wrong and which question? I think there's 20 simulations on the screen total. In the next simulation, how many do you get wrong? How many do you get wrong? And then which question did you get wrong? There were 6 questions. And then which of the 6 questions did you get wrong? Which of the 6 questions did you get wrong? So there's 6 questions. We're looking at this group of numbers right here, right below that. Which of those 6 questions did you get wrong? Well, you got the first question right. So the first one, oh, I know what you're saying. I know what you're saying. You got one question wrong. You're right. There was one question wrong. I asked 2 questions. You got one question wrong. And which one was it? The second. Great job, Sarah. Sorry, it was my poorly worded way of talking about it. And I'd like for you to tell me, let's go to the very last simulation. Did you get all the questions right in the very last simulation? Did you get all the questions right in the very last simulation? Did you get all the questions right in the very last simulation? I think hours stay the same. I reset points, Connor. Well, you say which last simulation. Connor, nice job. I love it. You should see. I need to give Connor some more points. Correct. In that very, very last one, you didn't. This one you did. Tell me if I make a mistake on here. If I'm highlighting it, it should all be correct. So that's 1, 2, well, 2, 3, 4, 5, 6, 7, 8. Does this look accurate? Does this look accurate right here? Did I highlight the simulations where there was at least I purposely did not make this mistake, but I did. That's why you check your work. 9. Does this look accurate now? I've highlighted the ones where we get at least one question wrong. I've put red markings on the ones where we get at least one wrong, and I've highlighted the ones where we get them all correct, and then I've counted how many trials out of the 20. So when we do the mathematics here, we want to know what percent of the time do we get them all correct, and that should be it right there. So we should have 45%. I believe so too. I think I've done it correctly. I think I can. So I think I've done it. We'll find out the hard way right here. 45%. Yes, fantastic. And you know what's really interesting? You're welcome, Sarah. You're welcome so much. Here's what's really interesting. I want to do this. So Connor, I hope you're still here for this, because watch this. Let's go here and let's make a vector of possible. So we're going to make a vector of possible right here. And we're going to make in this vector the rep function. And we're going to put here rep correct. And we'll rep correct 2 times. Or you know, we don't. We just need to rep correct 4 times. And then we rep wrong 1 time. Now, when you choose from this vector, if you sample from this vector, there is a 80% chance that you will get it correct. So here's just a random question. You got it correct. Here's another random question. Wrong, correct. So there's an 80% chance you'll get it correct. But we want to sample 6 questions, right? Let me check the thing. Sampling 1, 2, 3, 4, 5, 6 questions. And then what we're going to do is we're going to repeat. So let's replace equals true. And there we go. And then what we're going to do here is we're going to put this inside of a table. And now we see how many we get wrong. So that's just sampling 6. Sometimes we get them all correct. And then we're going to take the first value in the table, which is how many we get correct. And then we're going to go right here and go to for loop. Go I, 1 in 1,000, data. And then we're going to do this right here. This is the 32474 way of solving it. I should write questions like this. There we go. And then let's make a histogram of the data. It's going to be left skew because it doesn't meet the success failure condition. So you know what's really interesting about this? And I think this worked. There might have been a time when you got 0 correct, but I guess we could have taken that column. So there might be 1 error in my code, but there are times, I just want you to think about this theoretically right here. There are times where you're welcome so much, Sarah. There are times where you could study for a test and have an 80% knowledge and only get like 1 or 2 correct out of 6 questions. Like you on the practice test, you could be making an 80, and that would be like, you'd usually score up here. Like these are the most common occurrences around here. But with an 80% knowledge, it is possible that you would have only like 1 or 2 correct. That is possible, like theoretically possible. And so this distribution right here shows you the probability of these. And is it, Connor, what is it? Is it absolute? I forget how to change it so it's a percentage, which I wish I could just see the percentages and not the, but yeah, it is 100% possible that you could have this right here. So I think that's so cool how we can do the simulation right there and take a look at it. And yeah, that's a simulation. You could increase the simulation. I think there's a problem, Connor, with if you have 0 correct, because I think it would then only have 6 wrong. So that's probably going into this category over here. Because the data would show, ooh, that's interesting. That's cool. It's just keeping track of it. So I'm kind of my left. I love that kind of stuff. Let's talk about visualization number 8 for a moment right here. Visualization number 8 is when we're trying to make the differences between 2 means. And so we need to create a 99% confidence interval, include a short write-up. Cora, at some point, can we talk about how the interpretations for the interpreting the standard error for assignment 5? Yeah, let's do it right after this. You got it, Cora. I'll mention some brief stuff right here. So Sarah, if you're here, feel free to ask questions and we'll hop to Cora's question. Thank you for swinging by, Cora. So with this right here, oh, is it that it? Is that I knew it. There's so many arguments to remember. That looks to be it. It looks to be set to true. Yeah, there we go. There we go. Now we can see the frequency. It doesn't add up though, Connor. Something's weird about it. Because, you know, like this doesn't add to 100. So I don't know. I don't like it. It's not looking good. Is that right? Something just seems weird about that. So let's talk about... So with this interpretation right here, we need to make sure the conditions are met. So I just want to talk briefly about the conditions right here, because this is a new part right here for us. So Sarah, if you're here, feel free to ask questions, but let's talk about the conditions. So when we make confidence intervals or do tests, this is a big thing to know. I'm going to talk about the conditions right here for this part of it. When we do confidence intervals or when we do tests, you'll hear me say the following. So conditions for confidence intervals or tests. So whenever we do conditions for confidence intervals or tests, I'll always say condition 1, and then you'll do this. That'll be condition 1, random. Condition 2, 10%. And condition 3, or we pause. Someone will be screaming in the chat, pause, and I'll be like, yes, you get points for telling us to pause. So we'll pause right here because this depends on what kind of data we have. So depends on data. This one, since we're doing means, will be nearly normal. And 2 means independent. I think I have a flowchart with this. I need to find my flowchart and post it. But if we have quantitative data, it'll be nearly normal. If we have categorical data, it'll be success failure. You know what's really interesting, Connor? I think you're still here. Is this did not meet the success failure condition. So if it actually met the success failure condition, it would actually make a nearly normal distribution. Or if this was symmetric, it would also make the nearly normal distribution. Like if we had a symmetric type of distribution right here. So let's do 10 observations. Oh, what did I do this? There we go. So now since it's symmetric, there we go. So now it has enough occurrences to be symmetric. So that actually met the success failure condition. So this is actually a condition right here when we don't have enough success failures or the distribution, this will meet the success failure to be, yeah. But if you were to lower this, it would not have enough successes and failures. So we're actually seeing kind of visually right here, and that's an error with the way I'm doing it because of the way it's sampled. But because of this, yeah, I see what's going on. But because of this, we're not getting the correct shape of the data to use our tests. So what we're saying right here is these assumptions are super important to make sure. That's all I'm trying to point to, is that you have to meet these assumptions to do confidence intervals or tests. And if you meet the assumptions, that means you're going to probably have something where your data looks like this. And I want someone to describe the shape of this. And there's a hint on the screen right here, not that screen. I want someone to describe the shape of this using the hint on the screen, which is really important to make sure we have for a lot of our data. So think about what the shape is, and this is not technically the one we're doing right now, but it's one thing that's going to be very important for quantitative data especially. And it's going to be what? That the data is what? So we should see something with one of those conditions. And I did do random sampling. You sample less than 10% of the population. Nearly normal means. And this is the one I was talking about, the normal curve. This is technically success failure, but it does make like a nearly normal shape due to success failure for categorical data. And so we will go into much greater detail. Sorry, independent. We will go into much greater detail on these conditions right here, but these are the conditions for confidence intervals and tests for this one right here. So this is a huge hint. You do not need to put pause in your assignment. Do not write pause, but this is a huge hint for these right here. But you need to make sure you pause when you're doing these to make sure you have the right type of conditions based on the data. And since this is quantitative, so let me do this. Let me highlight this in another color here. And there we go there. And these are now data dependent conditions. So you don't always do you don't always do nearly normal. You don't always do independent groups. That's for two means. So two quantitative variables. So make sure you pause right here and then you do the data dependent ones. But these are always going to be random and 10%. Like these will always be random 10%. And then you pause and you make sure you do the data dependent conditions. So hopefully the color coding right here helps a good bit to understand. We're going to pause and make sure we have conditions that are proper. Have you done, ooh, that sounds like, oh yeah, I have seen that one. Send me some stuff on that, Connor. I have seen that. I haven't done it lately. I think I know which graphic that is. I think I know which one it is. Let's talk about standard errors. I do not have a model M in my graphics right now. Let's go here and let's talk about, so this goes out to Cora right here. There we go. Here we are. So when we talk about, awesome, Connor, awesome. When we talk about standard error, Cora, if you're in yesterday's class, you'll have a word for standard error. If you're in today's, which class are you in, Cora? Today's or yesterday's? I'll give Cora a moment to respond here. Are you in today's class or yesterday's class? If you're in yesterday's class, you'll know the word. If you're in today's class, you might be like, I have no idea for this word, Brian. So there's a word we always say when we have standard error. So we talk about the standard error. What do we use for the word standard error? It's a U word. Oh, that's all right. No worries. Oh, there's a U word we use for standard error. It's called uncertainty. And thank you, Cora. So you can just always say like, I don't know. Someone could, yep, hey, great job. It's uncertainty, which is like, I don't know. So I want you to think about this here for a moment. It's going to be easier to look at this one right here. And I'll explain why in a moment, because this will help out with the last question also. You think, so imagine this. Well, let's just talk about yesterday. You said someone was moving into your house, right? So they say, I'm going to get there at 3, but I could be off by about 10 minutes. So I'm going to get there at 3, but I could be off by about 10 minutes. Which of those is the estimate and which of those is the uncertainty? They say, I'm going to get there at 3, but I could be off by about 10 minutes. What is the estimate and what is the uncertainty? So they say, I'm going to get there at 3, but I could be off by about 10 minutes. So which one of those is the estimate and which one of those is the uncertainty? When they say I could be off by about 10 minutes, are they saying they're going to get there at 2:50 or 3:10? No, they're saying, I don't know, like I could get there at like 2, like 3 is the estimate and 10 is the uncertainty exactly. So if they got there at 3:11, would you be like, wait a minute, you said you could be off by about 10 minutes? They're like, yeah, about 10 minutes, about 10 minutes. If they get there at 3:04, you wouldn't be like, wait, you said you could be off by about 10 minutes. You'd be like, oh, that's kind of within your uncertainty window. Does that make sense what uncertainty is? Like, I know, like, you're like, I know what uncertainty is, Brian, but this is the same thing. You're saying, I think the slope is this. You're saying, I think the slope is this, but I could be off by about this amount. So this is the amount you could be off by. Does that make sense right there? So this is the amount you could be off by. And we're going to round this right here to 56.4. I know that's like a weird round, but it'll be really nice in a second. And then the second one, we're going to use this right here. I know this is not the slope, this is the intercept, but it's nicer numbers than the slope. Let's go to our million of data sheets open and go to this. Okay, so we were estimating the slope right there. I mean, the intercept. And we'll talk about the slope here in a second. This is 201, 201. Say hey. So you told me that you said, I think the intercept is 56.4. But I could be off by about 0.6. So you said you could be off by about 0.6. Do you remember the 68, 95, 99.7 rule? We are using the empirical rule right now. And what can we make with this? What can we make? And this actually ties into the assignment they're doing. What can you make with the empirical rule for your estimate? What can you make for your empirical rule with your estimate of the intercept or the slope? You could make what for the estimate? So here's you're making something for the estimate. Confidence intervals, exactly. because you're saying, I think the slope, the intercept is 56.4, but I'm 68% confident it's probably between here and here, 95 between here and here, and I'm 99.7% confident it's between here and here. And I want us to focus in, let's do the 95% confident because this is helpful later in the assignment. If I go ahead and remember these numbers, 55.2 and 57.6, if I go back to R and I say confident for the model, let's go here to confident. So confidence makes confidence intervals for the coefficients. We talked about this a little this morning too. Remember those numbers we just saw were 55. Was it 55.2 exactly? Number 12, right? 55.2. Look at that. 55.2 and 57.6. We were off by only 1/10 on this one. On the lower one, we were off by a hundredth, and on the upper one, we were off by 2/100, or by just a tenth. So I'd say that's pretty good estimates. Using this right here, just with estimates, we were able to make a 95% confidence interval. And what did I do to make a 95% confidence interval with this output right here? So what did I do to make a 95% confidence interval? I basically went up and down 2 whats. So I took my uncertainty and I just went this, and I took my uncertainty and I just went this to make a 95% confidence interval. I took my estimate and then just went up and down whats. Good to see you here, Kira. I took my estimate and went up and down 2 whats. Well, that's... So you can see it here visually. Standard errors, which are just our uncertainties. Standard errors are basically like variation that could exist in our, like we're saying like, well, here's our estimate of the slope, but I could be off by about this much. I'm not saying I am off, but that's just kind of like, well, plus or minus that. And if we go up or down 2, what did I just compute right here by doing all of this? By doing all of that, I just went up and down 2 uncertainties, and that's going to be very, very close to a what interval for the slope. And then we're going to do a direct interpretation. So these numbers I have are probably the bounds of a what. Those numbers right here are probably the bounds of a what. Oh, that's awesome, Kira. That's so good. I'm so glad to hear that. And these numbers right here, because I went up and down 2 uncertainties, and now we're doing the slope, not the intercept. We're doing the slope, so we're trying to estimate the true slope. So since I went up or down 2 uncertainties, and those numbers on the graphic no longer apply because those are intercept estimates. I went up or down 2 uncertainties. I have just made a what interval for the slope. We're very close to it, 95% confidence interval, exactly. And it's going to calculate it more exactly for us. It's going to use better calculations, but look at this. I would have estimated 0.066. It does this. I would have estimated 0.08. I mean, that's off by like, it's so small what it's off. It's a more finer calculation, like there's decimal places we're not carrying, but it's basically 2 standard errors. There's very technical things like about sample size, like technical, but it'll calculate it for you, and it's just making the 95% confidence interval. So what you're telling me right here, Cora, is that this uncertainty is what? When you have an estimate of the slope, the uncertainty is going to tell you, or the standard error, I'm just calling it uncertainty, is going to tell you about how far your slope might be away from the true slope. Does that make sense? Because we're trying to estimate, let's look at the graphic again here. We're trying to estimate the true slope, and we're making an interval using the uncertainty. So when we use this uncertainty right here, we're saying, I think this is the true slope. Like that's my estimate of the true slope. Like it's my B0 and B1, excuse me. This is my estimate of the true slope. So it's my best guess of the true slope, but I could be off by about this amount. It's your amount of uncertainty in your estimate of what you think the true coefficient of the slope is. Does that make more sense, Cora? It's a little more of a direct answer right there. And then we use that uncertainty to make confidence intervals, and the amount of uncertainty we're willing to go out would allow us to be more confident that the true value is contained in our interval. The true slope would be contained in the interval. Like we can go from 68 to 95 to 99, and you can change that pretty quickly here by going to levels equal like 0.68. And so that one will come in, and then we could make it wider by doing this. You can put any value in there. You can do that, and that'll be really wide. Awesome, yeah. So you see you can control the level of confidence, and look, as we get more confident, the interval gets wider. Last question right here. As you get more confident, the interval gets more and more wider. Like I just made a ridiculously confident interval. Wow, it's actually still doing that? I made it so confident it gave me all the values. It eventually broke it, and it said, okay, if you want 100% confidence, it would have to be between infinity and negative infinity. So, which shows the concept that if you want 100% confident, you'd have to have all values. Then you would know. So that's ridiculous so we just entered in a confidence of 1, basically. It rounded it on us. It rounded it up to 1. It's if you want 100% confidence. Would you want us to mention confidence intervals when discussing? You can do it. As long as if the grader takes off points, let me know. We want to make sure you can communicate these things, and hopefully I'm communicating them, because if I can't communicate them, we're all kind of in trouble. But the grader is meant to kind of look over, are you communicating these topics in a way someone would understand? Do you have applied knowledge of this? We don't want you to just like memorize stuff. We want you to be able to communicate it and know that you understand the concept. So if you give a good discussion on it that shows that you understand that the amount of uncertainty that we have in our estimate. So I'm saying the slope could be this value, cite the value, but I could be off by about this amount. Now, do you want a lot of uncertainty in your slope, or do you want a little bit of uncertainty in your slope? Now, remember what the slope is used for. The slope in regression is used for statistical significance. So would you rather have like a slope with a lot of uncertainty? Let's look at that. Here is a slope, and I have these on the graphic still. Here's 2 slopes that both look like this. The first slope could be off by just a little bit. Like maybe it's from here to here that the slope could be. So the first slope is probably in between there. The second slope is could be between here and here. Like it could be way stronger or way weaker. So which would you rather have? A little bit of uncertainty or a lot of uncertainty in your slope estimate? Would you like? You want as little uncertainty as possible, because if you had a lot of uncertainty, what might be the value of the slope? Because look at what this goes through, and I'll give you a hint. If you have a lot of uncertainty in your slope, then what might be the slope if you had a lot of uncertainty? Like if you have too much uncertainty, then the slope could be this value. You'd be like, well, I mean, maybe it's negative, maybe it's positive, but it also could be what? If you have too much uncertainty. And then that other highlighted portion is actually very important too. Because then we run into that issue, and it's like, okay, we have so much. And if your slope is 0, then your line explains nothing. So now, because you have so much uncertainty in your model, you're like, my model's not statistically significant. It's the same as the naive model. So you want as little uncertainty as possible. So both of these models, model 1 and 2 here, have the same slope. Like they both could have an estimate of, let's say, 10 for the slope. And this one has an uncertainty of, let's say, 1, and this one has an uncertainty of 10. So interestingly enough, and this is what's so interesting, like, is it really interesting, Brian? Yes, it is. So we could compute the t statistic here. This has a t of 10, and that's going to make it a p-value of basically 0 for all intents and purposes. This one has a t with a large enough sample size of 1. How am I getting this? 10 over 1, or 10 over 10, excuse me, and this one's 10 over 1. That's how I'm getting those t statistics right there. And then the p-value on this one is equal to 0.32 or 0.3231 something. It's going to round to about, I'll use this because that's the version we'll know. And why I'm getting that is the following. This is the answer right here. I'm getting it because we're plotting the area outside of 68. So here's your t statistic. Your t statistic would be here. And you do the, excuse me, so your t statistic's here with 1. And then the absolute value of your t statistic is here. And then the area outside of it is this, and that's the p-value for your test. So we're doing a lot of similar topics in 320 and 201, but the computer does it for us. We don't need to calculate the p-value. We should understand how the t statistic's calculated and a little bit about the p-value. Does this make sense here, Cora, how I kind of, this is a little more advanced, like we don't have to calculate this. It's all done for us right here when we do the summary. So it does the t statistic, which is just the ratio of these. The t statistic's just going to be your estimate over your uncertainty, and it does that for us. And these t's are so crazy that the p-value is basically 0. How's everything looking right there on that? A lot of great questions today. A lot of good 320 stuff. Awesome, yeah. And this, if you graphed this just really quickly, if you were to draw out this p-value, it would look something like, it'd be ridiculous. It's a p-value, it's a t statistic of 20. It would look, you'd be all the way over here, and then this would be the other side of it, and you'd have to plot the area outside the normal curve here, and it's basically 0. Unrelated question, if we have a question about points that were taken off on assignment 4, email me. I am the final say, and there's basically no area with a t of 20 right here. So the t value being 20, and an absolute t, just as extreme as absolute t equal to negative 20. Like, So yeah, it's now. Yep, Cora, email me. I will take a look. I think that's got it. Let me play some music. Music. It's too sad. I need to take that one off. I think it's too sad. Don't want too sad. Want chill. Well, that's got it. I'm gonna answer some emails. Cora, send it my way. I will take a look. I am the final say on all grades. Graders can take off how many points they want, and I can give them back. I am the final say on grades because I'm the teacher. I get to do that. I do think the graders are doing an excellent job, though. Thank you to the graders. They're keeping up pretty well with the work. They're doing a great job. It's a lot of work, and they ask a lot of questions, which I like. So, but I'm not perfect. They're not perfect. And a lot of times I agree with them. Sometimes I disagree. And I get the final say. Awesome, Cora. Thank you so much. Great work today. Keep it up. I'll talk to everyone later. Bye for now. Bye.